Hello, my name is Kevin Chen, and I'll be presenting alongside Nithin Shrivatsav regarding our research work on learning hierarchical task networks with preferences from unannotated demonstrations. Traditionally, HTNs are often handcrafted and require significant domain knowledge and engineering effort. We present a method to procedurally learn HTN structures from unannotated human demonstrations. We contribute the CircuitHTN algorithm, which enables unsupervised learning of HTN for human demonstrations, resulting in a model that preserves the user's action selection preferences. CircuitHTN first converts user demonstrations into an action graph. Then, CircuitHTN uses the action graph to construct an equivalent resistor network. This is the key insight of our work. We use a directed acyclic graph reduction technique that is analogous to reducing electrical resistor networks. CircuitHTN then uses this reduction technique to convert the resistor network and corresponding action graph into an HTN. In certain cases, the resistor network cannot be simplified using established reduction methods. The naive CircuitHTN version of our algorithm fails in these cases. We have developed extended CircuitHTN, which can handle such situations by restructuring the resistor network to enable reduction. Let us walk through an example. We first build the equivalent resistor circuit for a given action graph, as shown in the diagram with the resistors. Then, we use rules for reducing a resistor network. There are two rules for reducing circuits. Two resistors that are either in parallel or in series can be combined into a single resistor. Coming back to our problem, we can use the rules we have described to combine R3 and R4, which are resistors in parallel. We combine the equivalent nodes in the action graph with a decision node. Here, we see R3 and R4 combined with a decision node. Next, we combine R2 and R34, which are in series. We combine the two equivalent nodes in the action graph with an abstract action node. And this is the result. Next, we combine R234 and R5, as they are resistors in parallel. We combine the two equivalent nodes in the action graph with a decision node. And this is the result. We notice that the remaining resistors are in series, so we combine the remaining nodes in the action graph with an abstract action node. We are left with one resistor, so the resistor network has been fully reduced, and we have produced our HTN. We note that there are some edge cases in which the action graphs and the equivalent resistor network cannot be reduced with series and parallel reduction techniques. The example network here has no pair of resistors in series or parallel. To solve this case, we have developed extended CircuitHTN, which will restructure the action graph. I will give an overview of how it is done for this example. We run the first common successor, or FCS algorithm, to find reconverging paths in the graph. FCS will identify the nodes R1 and R6 as the source and sink nodes of the subgraph containing reconverging paths. Note that the simple paths from the source and sink nodes go through the node R3 twice. Thus, extended CircuitHTN duplicates node R3 and restructures the graph. This is the result of the restructuring, and now we can perform our reduction rules for combining resistors in parallel or in series. In summary, CircuitHTN procedurally learns an HTN from human demonstrations. We convert the human demonstrations to an action graph, then to the equivalent resistor network, and then finally to an HTN. Naive CircuitHTN uses rules for the problem of reducing resistor networks to reduce the action graph. Extended CircuitHTN extends naive CircuitHTN by restructuring the network when the network is irreducible under certain circumstances.
Hi, now let's look at some evaluation and results. We compared our approaches, which are the naive CircuitHTN and extended CircuitHTN, against two prior works, the click chain HTN and the probabilistic HTN, and we evaluated these approaches on two tasks, a table setting task and a salad making task. Here we show 6 out of 10 demonstrations that were collected from human subjects for the task of setting up a table in the Oral Bench simulator. Here we show the robot executing a specific plan from the learned CircuitHTN, and the blue nodes are primitive actions, whereas the gray nodes are abstract actions such as sequence nodes or choice nodes. In summary, the metrics we use to compare the four approaches include preference alignment, structure, completeness, and soundness of the plans. Based on the results we obtained, we infer that extended CircuitHTN is the only algorithm which can convert complex demonstrations to compact hierarchical task models that accurately represent action execution preference and can generate sound and complete plans. Please refer to our paper for a detailed analysis of the computational characteristics of all the tested approaches. Thank you for your time, and we are excited to take on any questions.